Thank you for the extremely kind and generous introduction. Thank you for the invitation. It's a great pleasure to be back here. I was only here once before, and that was something like 14 years ago, and the place has grown immensely. It's nice to catch up with old friends and meet a bunch of new people. And as Jean-Vin says, whether you're a theorist or an experimentalist, you have to talk to me, but he got the reason wrong. The reason is that I need to learn what you're doing, and I really want to learn what as many people here are doing as possible. Today, I'm going to try to tell you what I describe as everything you always wanted to know about quantum tunneling and photon propagation, but were afraid to ask, maybe didn't even think to ask. Hopefully, some of you will tell me you had some other questions that you were afraid to ask that I don't answer here. We can talk about them afterwards. And I'm coming from the Department of Physics at the University of Toronto and the Center for Quantum Information and Quantum Control. The view from our department looks something like this, a mix of an old-style imitation of Oxford and Cambridge, and something that looks like a slightly less modern Singapore. We're actually about the same size cities. But this is what our group looks like. And I just want to put up some of the names of the people who've gone through the group in the past years and been instrumental in the work I'm going to be describing. So in case I forget to repeat their names at each juncture, you've seen them here. The work I'm going to be telling you about now is really largely due to Ramon Ramos and David Spearings on our atom tunneling experiments, picked up more recently by Joseph McGowan and Nick Mantella. And where is he hiding? Josiah Sinclair and Daniela Angulo Murcio on our photon storage experiments, picked up by Kyle, Vida Michelle, Andy, and a bunch of others. But of course, over the years, many, many other people have contributed to getting these experiments into the current state. And we're going to need many more people to help us continue that looking ahead. So I do want to say we're always looking for interested grad students, postdocs, or just visitors to come spend some time in the group. In fact, He Shang here was recently visiting and really instrumental in some of the other work we were doing. So please reach out if you or you know might be interested in coming to Toronto for a while. Before I describe these two specific experiments I really want to focus on, I just want to give you a sense of our longstanding obsession. The question that keeps me awake at night about quantum mechanics is what I like to call quantum archaeology. What can we say about the past in quantum mechanics? And I think we've all been taught the same story about quantum physics, that if you give me the wave function, that's as much as you're allowed to say. You can't say anything else. But of course, afterwards, you might make a measurement and learn more. And my question is, once I learn more, does that give me extra information about what was really going on? And this goes back to these famous discussions of which way information and delayed choice, things that Wheeler is famous for popularizing. You have some interferometer, and if you don't measure which path the photon took in the interferometer, you just see it on the screen at the end. Ever since Bohr, people like to tell us you're not allowed to ask which path it took. And that's very, very different towards what we do in every other branch of science or in our everyday lives. We dig up some fossil, we draw conclusions about what this dinosaur was doing 65 million years ago. No one questions that. But of course, most of us nowadays believe that that dinosaur obeyed the laws of quantum mechanics. So when you do that, you are saying, I'm getting new information about what a quantum system was doing in the past by making a present observation. So my big question, and that of a lot of people that I've been working with and following on, is what are the limits to what we can say about the past in our quantum mechanical universe? How much do we learn from a new observation about what was already happening before we made the observation? So there's a simple example, pointing this the wrong way, that we like to think about. And I won't go through it slowly. I'm happy to talk to others about it over the next week in more detail, anyone who wants. But you can imagine putting a particle in a superposition of two states, of two boxes, A and B. And if I now ask you, where's the particle, you know perfectly well, there's a 50% chance I'll find it in A, 50% in B. That's all I can say. Our question is, what if I now tell you more? What if I now tell you, I look for the particle later on, and I find it not in A or B, but in a new superposition, B plus C. Given that new information, is there any more that you can tell me about what the particle did before I observed it? And I won't go through trying to poke and prod you and see your intuitions. Most physicists react by saying, we're not allowed to ask questions like that. It really was 50% in A and 50% in B until the moment you made the measurement. And then something none of us understands happened. There was an uncontrollable, irreversible disturbance, and now it's in this new superposition. But in fact, based on a formalism due to Yakir Aharonov, David Albert, and Lev Weidman, we have ways of calculating things like what was the probability of being in B or A or C between this preparation and this post-selection. And it gives fascinating answers. In this case, for instance, it says the particle was definitely in B, and there's a measurable sense in which that's the right answer. It turns out that's not so surprising if you redraw this as the kind of experiment we would do in a quantum optics. If I wanted to do that experiment, we've done something like it, I would say, well, let's take a photon, my favorite particle, prepare it in a superposition of masses A and B. Well, that just means I fire it at a beam splitter and let it follow a superposition of two paths. But later, let someone else look for it in a superposition of B and C. How would they do that? Well, they'd combine B and C at another beam splitter and place a detector over here. And the original question turns into, if I emit a photon over here, and my colleague detects it at this detector, how did it get there? Was it really 50% in A, or was it ever 50% in C? I think from the picture, the answer is obvious. At least to experimentalists, it's obvious. I'm not sure if theorists have a different intuition, but everyone I know would admit the particle must have been reflected here, and followed path B the whole way. So that's what comes out of that Aharonov formalism. There's a way of calculating this directly. Of course, this isn't a complicated case. The interest of the formalism is that you could make any arbitrarily complicated initial state, any arbitrarily complicated final state, and still ask, what did the particle have to do to get from one to the other? What do I learn when I do this post-selection? So I think you'll see how that comes back in both of the experiments I'm going to describe. So let me now jump into those experiments. Here's the outline of the talk. I'm going to give you an introduction to this atoms and light experiment and introduce the 100-year-old controversy of how long a particle takes to traverse a quantum mechanical tunnel barrier. I'll then tell you about our experiment, where we actually measured that a few years ago. This was something I'd been aiming to do for about 20 years or even more. My white whale, as Rob Speckins would say, and we finally harpooned the whale. We're not quite done, though. We're still chasing the whale. And I'll tell you a little bit about two other experiments that we're hoping to do in the next few years based on this. After that, some of you will have lost track of what I'm saying, so I'll switch gears and start a new topic and try to wake you back up, and we can try a second time. And I'll tell you not about atoms and light, but about light and atoms, a more recent series of experiments where we ask, when a photon traverses an atom cloud, how much time does it spend actually trapped inside the atoms? And hopefully you'll see what I mean by that. All right, so on to the tunneling for now. You've all learned about quantum tunneling. This is my favorite video of it. One time in 100 or 1,000,000, of course, the coyote gets to the other side. And we've all learned how to calculate how big this wave function is. What is the probability of appearing on the other side? What we don't learn how to calculate is how long does the particle take to get to the other side? And it's not that people haven't asked that question before. They've been asking it since at least 1932. My guess is they've been asking it since 1926, but they didn't have any answers they were ready to publish. So we only know about from 1932. It remained controversial ever since then. There's no good semi-classical way to calculate it, of course, because as you lower the energy of a particle down to the top of the barrier, the kinetic energy is just the difference, E minus V naught. And as it goes to zero, the kinetic energy goes to zero. You'd expect semi-classically the velocity to vanish and the time to go to infinity. That's the semi-classical solution. As you get below the barrier, the kinetic energy would be negative, implying, I don't know, an imaginary momentum, an imaginary velocity. We really don't know what to do with that. So we need some other treatments. And of course, we know how to treat the problem better. You can just go to Wikipedia and download this animation. You can simulate the Schrodinger equation yourself, but you don't need to because someone did it and posted it on Wikipedia for me. And in principle, I could look at where this peak is on the way in and measure exactly where's that peak on the way out and calculate how long does it take before the peak at the exit appears. This is similar to what we're used to calculating in wave propagation known as the group velocity. And of course, we know how to calculate the group delay analytically. We typically do it using the method of stationary phase, which hopefully most of you are familiar with. Whether or not you are, the important thing is the method of stationary phase is related to the phase of the wave function. So if you know how that phase behaves, you're going to learn something about the time delay. Well, we know how the phase behaves inside a tunnel barrier. There's e to the ikx propagation entering the barrier, e to the ikx exiting the barrier. But inside the barrier, there's exponential decay, also exponential growth. No accumulation of phase, which means that the phase of this transmitted wave becomes essentially independent of how thick the barrier is. And the interesting thing is that implies that anything you calculate from the phase, like this group delay, also becomes independent of the thickness of the barrier. And this was what was realized in the 30s and again in the 50s. And then finally, the point was sort of driven home by a guy named Hartmann in the 1960s, that the time delay becomes independent of the thickness of the barrier, which is very, very disturbing because as d goes to infinity, eventually t will be less than d divided by c, the thickness of the barrier divided by the vacuum speed of light. So it looked like this suggested faster than light propagation, and people said there must be a problem. The Schrödinger equation is non-relativistic. Let's use the Dirac equation or Maxwell's equations. Same result. That doesn't solve the problem. Well, maybe the stationary phase approximation breaks down. Let's do more careful calculations. Nope, that doesn't resolve the problem either. It turns out that the peak really does appear faster than it would if it just traveled at the speed of light. Now, very little gets out in this peak. Most of the energy, in fact, gets reflected. And if you're a little more careful about it, you find that the information doesn't really track the peak either. So people eventually came to terms with this and said, all right, the prediction is correct, but it only describes where the peak is. And maybe that's not the most interesting question. For me, it's not the most interesting question. What I want to know is, what was the particle really doing? How did the frog cross the road? Is it really always just described by this wave packet, mostly reflected some here, until that instant when you detect it transmitted, and then it magically all jumps to that side? Or, like in the case of that three-path interferometer I drew before, the three-box problem, do we learn something new about the history when we see it transmitted? Should we really say the particles that are getting reflected behave one way, but the particles that eventually get transmitted behave a different way? And we learn something about that doing a real experiment in the laboratory, or perhaps using the right kind of mathematical formalism. This is really a question that Marcus Büdeker and Rolf Landauer, two very famous condensed matter physicists, started asking very vocally in the 1980s. And they were concerned about real tunneling in semiconductor devices and superconducting devices and trying to understand what are the relevant timescales. And they saw this business about the peak and pretty quickly said, that's just not the right time. It's not the physically relevant time. Let's look for something more important. Let's try to think of ways that a particle tunneling through a brick wall here could carry the right kind of stopwatch, and we could measure what is that stopwatch. And there have been many, many different approaches. Back in the late 80s, Daniel Estève's group in France did a beautiful experiment using basically the ancestor of today's superconducting chips, using macroscopic quantum tunneling of a Josephson junction to probe one of these indirect timescales. Büdeker and Landauer really liked that result, but it left a lot of room open for other groups to look at different definitions, different clocks, different interactions. This has been done with neutrons, with photons, with superconductors, with atoms trapped in lattices, et cetera. In the past 10 or 12 years, perhaps the most famous approach has been the one pioneered by Ursula Keller, who uses ultra-fast photoionization of atoms to probe how long the electron spends in the forbidden region. That led to a lot of headlines. We have our issues with their work, but it's really, really interesting. And I'm going to tell you about one of the earliest theoretical proposals and how we implemented it with cold atoms. So the idea here is to somehow measure the time an atom spends in a barrier, but to do it gently, to do it what Horonov's group would call weakly, in the sense that when I probe the atom, I don't want to disturb its evolution. I want it to be able to keep tunneling. So we need to do something with a very, very gentle interaction and then average those results to see what's going on. One of the earliest ideas for doing this again, popularized by Büdeker in 1982, but going back to Bose and Ryabchenko in the 1960s, is to use Larmor precession as a kind of clock. So here's the idea. Imagine a one-dimensional square barrier, rectangular barrier, simplest tunneling case you can imagine. But let us have an electron tunnel through this barrier. Well, the electron also carries spin, so we could imagine it initially polarized along the x direction. As it propagates towards the barrier, the spin is not affected. But now if inside the barrier we add a magnetic field along the z direction, then while the particle is in the barrier, it sees that field and it precesses at the Larmor frequency. So when it gets out, the spin will have a slightly different angle. And we interpret that angle as the Larmor frequency multiplied by the duration of the interaction between the electron and the field. So how much time it spent in this region. So that's what I've wanted to do basically ever since I finished my PhD. The problem is I don't know how to get single electrons to tunnel through square barriers. I certainly don't know how to confine magnetic fields to angstrom scale regions and do this. But we realized that with cold atoms, you could get there. So here's a schematic of the experiment we ended up doing. We Bose-condensed rubidium-87 and then cool it further to about 1 nanokelvin, at which point it gets a coherence length or a thermal de Broglie wavelength of about 4 microns, which is really nice because we know how to build potentials for atoms out of light. And light we can focus down to 1 micron or even better. So we can make a repulsive barrier for our atoms by focusing this blue laser beam at 420 nanometers down to a 1 micron Gaussian. I would have liked a rectangle. We can do a Gaussian for now. And make sure that the atoms have a coherence length much longer than the scale of that potential. So we're in the right regime to study quantum effects like tunneling. So we put this atom cloud inside a crossed dipole trap. So here we have a red beam that attracts the atoms, a second red beam that attracts the atoms that get condensed in the intersection. And we add over here this blue beam that's going to repel them. The barrier height of this beam corresponds to about 150 nanokelvin. So much, much higher than that 1 nanokelvin temperature of the atoms. It corresponds, though, to an incident velocity of about 4 millimeters a second. What I mean by that is if a rubidium atom moves at 4 millimeters a second, its kinetic energy is about 150 nanokelvin. So if I fire an atom at this laser beam at a velocity of 5 millimeters per second, it rolls over the barrier and keeps going. At 3 millimeters a second, it gets entirely reflected by the barrier. But around 4 millimeters a second, half get transmitted, half get reflected. We can really study the quantum tunnel. There's a picture in a slightly different geometry, actually a movie of our atoms. The colors are false. This is an absorption image of an atom cloud sitting on top, basically this blue barrier, and being pulled down just by the force of gravity. And what you see is initially a big cloud goes through. Those atoms were too hot. But once they go through, everything sitting on top of this blue light table is held there by the repulsive force of the light until it spills out over the edges. Except, of course, for a few that must be tunneling through all the time. But we didn't have the resolution to see them in those days. Afterwards, we developed the low enough temperatures that we could start probing them. So the one other thing we need is this fictitious magnetic field. The reason we decided to do this with atoms is because instead of using real magnetic fields, we can use any other interaction that couples 2 different levels, right? That's mathematically equivalent to a magnetic field. And if we do that using laser light, then we can confine it to that 1 micron region or even more tightly. So we use a pseudomagnetic field that couples the F equals 1 m equals 0 and F equals 2 m equals 0 states of rubidium. It's a 2-photon transition. So really what's going on is you absorb a photon and go up to an electronically excited state and emit and come back down. But the energy difference between those 2 optical photons is just enough to leave you with this hyperfine energy shift of about 6.8 gigahertz. For those of you who aren't familiar with it, this is exactly the kind of transition that's used in atomic clocks. This transition in cesium is the current definition of the second. So these are used because they're so highly controllable, precisely known, and relatively insensitive to environmental effects. So we chose to use the same thing for the tunneling. What we'd like to do is superpose that pair of beams, known as Raman beams, right on top of the barrier. In fact, since this was technically difficult, we cheat. So far, we focus our barrier beam down to 1 micron, but we also modulate the barrier at 6.8 gigahertz, creating an extra sideband. So the barrier itself contains the second sideband that will drive that two-photon transition. That's for the initial version of the experiment. So now, as you tunnel through the barrier, you're also undergoing this pseudo-rotation. So when we put that all together, this is what the experiment looks like. We begin with our Bose-condensate in this crossed dipole trap, extra cooled using optical lensing down to that 1 nanokelvin temperature. We then turn off one of the traps, so the atom is now sitting in a one-dimensional guide. It's basically like a fiber optic for the atoms, which we intersect with the blue-detuned beam, which we also modulate so that while you're in the beam, the spin can precess. And that way we'll have a measure of how long the atom spent inside that beam. We then give the atoms a little kick. We do that with a magnetic gradient. We kick them at a few millimeters a second. Some are transmitted, some are reflected. And now we can do Stern-Gerlach imaging or some other polarization sensitive probe to measure what is the spin of that transmitted cloud. The very first experiment where we did that, we managed to turn off the barrier so that we could just calibrate this clock on atoms moving through free space and measure how long do they spend in a 1 micron region as a function of the initial kick we gave them. And what we see is as you lower the incident velocity, the precession angle, so this measure of the dwell time, goes up. And in fact, it goes up as 1 over the velocity. So this is a very, very difficult, expensive, time-consuming way of measuring that the time an atom spends in a region in free space is given by the thickness of the region divided by the velocity of the atom. But it allows us, of course, to calibrate our clock, right? And to confirm that things are working as. This is a real picture of the two different spin components of the atom separated in space. So by looking at these absorption images, we can measure how much is plus X, how much is minus X, and that's how the angle is extracted. When we repeat that with the barrier, we get transmitted atoms split into plus X and minus X, and also reflected atoms, which are split as well. And we can measure this ratio. When we originally did it, we saw something very dramatic, but I don't want to mislead you. There's a reason it looked more dramatic than it should. We saw these numbers go up, and over here, 5.1 millimeters per second was our barrier height at the time. That was our critical velocity for tunneling. So semi-classically, if we sent particles in at 5.1 millimeters per second, they would have 0 kinetic energy on top of that Gaussian. The velocity would go to 0, and the time would go to infinity. Of course, quantum mechanics abhors infinities, except for quantum field theory. So this doesn't go to infinity. There's some finite result. And more than that, as we go to lower and lower velocities, the time seems to start getting smaller instead of continuing to grow. Now, as I said, this turns out to be misleading. Take it with a pillar of salt. There's a reason for it, though. And the understanding goes back yet again to Büdeker. He figured this out in the 80s. If we think back to this Larmor clock, why is there precession? How would we analyze this mathematically? Well, this X-polarized spin can naturally be decomposed into a more convenient basis. I have a magnetic field along Z. That's the natural quantization axis. The Hamiltonian is diagonal on the Z basis. I should really think of this as being a superposition of spin up and spin down. Now, of course, when spin up and spin down go through a potential that has a spin dependence because of the magnetic field, they'll pick up different phases. And the phase difference between up and down is what gives you the precession angle in the equatorial plane. So that phase difference is really what this was designed to measure. And that might sound familiar from my discussion of the stationary phase method early on. It's not exactly the same time, but there are very close mathematical connections between the two. The problem is that one of these particles sees a lower barrier because it's aligned with the magnetic field, and the other particle sees a higher barrier because it's pointing the wrong way. So we're disturbing the tunneling by adding that magnetic field. Now, Bose and Rybachenko understood that perfectly well, and they said, let's use a very, very small magnetic field so that we don't disturb the particles very much. In fact, let's take the limit as B goes to 0 and to see if the ratio of the angle to the Larmor frequency is well defined in that limit. And it is. The problem is that, as Büdeker calculated, the ratio of the transmission probabilities for the spin up and the spin down is also affected to first order by that magnetic field. So even in the limit of B goes to 0, it turns out there's more of an effect tending to preferentially transmit the spin up rather than the spin down than there is a precession in the equatorial plane. So Büdeker looked at this and he said the problem with the earlier treatment is there isn't only one Larmor time, there are two. There's the precession in the plane and there's the alignment towards the z-axis. And we must consider both angles. So I don't know what to do when you get two different times. Büdeker's approach was just to add their squares and take the square root. It seemed natural, but there's no deep reason for doing that. What's more interesting to me, and I think just confusing in the 1980s, is that there was other work by people like Sokolovsky, Baskin, and Connor, and a few others, which were very, very abstract, mathematical approaches, no attempt to connect them to things you might measure in the laboratory. This one in particular used a Feynman path integral, which means integrating over a exponential of a complex action. And in the end, it gave complex results for the time. So of theoretical interest, but most people dismissed it as having no relationship to reality until this Büdeker work came out. And it turned out that these two components, this in-plane angle and this out-of-plane angle, are exactly equal to the real and imaginary parts of the time calculated by these guys. So in fact, it seems like there is some broader picture of the time that requires two different components that we could think of in terms of three-dimensional geometry, we could think of in terms of complex numbers. My feeling is that these can all be unified by looking at that weak measurement formalism I mentioned from the beginning, Yakuya Aharonov's formalism, which also gives real and imaginary parts to things that you measure in post-selected situations. The post-selection here being that we're only looking at the transmitted particles. But in the context of weak values, because they're defined based on a measurement protocol, we actually know what the physical significance of the real and the imaginary parts is. The real part is really telling you how much did the pointer shift when you coupled it to this system. And in this case, the pointer shift is the in-plane precession. It's what you always expected your electron to do. The imaginary part is related to the fact that quantum mechanically, there's always a back action. The measurement can always disturb the system. And it's really not a measure of how much effect the system has on the pointer, but rather an effect of how much effect the pointer has on the system. So that's why there are always these two parts. So we decided we needed to measure them both. And clearly, if you're rotating in three directions, it's not sufficient to just look at the projection onto that initial axis. You've got to do the full three-dimensional tomography. So my very heroic students at the time, led by Shreyas Potnis and Ramon Ramos, figured out how to do very accurate tomography of that pseudo-spin in the hyperfine sector. And as you go from high velocities, indicated in green, to lower velocities indicated in red, what you see is we began polarized along the x-axis, and you begin to get more and more precession towards y, but after a while, you start to just move towards minus it. At low enough velocities, what's transmitted is just essentially the aligned component of the spin. So we can look at the different projections. From the XY projection, we can extract the real part of the time, this in-plane precession angle. And from the XZ, we can extract the out-of-plane, which is the back action, the imaginary time. So here is our very first busy plot of this. It came out about 5 years ago. We were excited that we could even get below the tunnel barrier at all and measure both of these times. But I have to admit, the temperature was so high that when we looked at these points as far below the barrier as we could get, we estimated that about a third of the particles we were seeing weren't even tunneling at all. They were actually just from the high energy tail of our thermal distribution. So we're really averaging over a lot. And you see the error bars here are pretty big. But there's this tantalizing idea that as you lower the velocity, the time begins to go up. And instead of diverging like this Büdeker-Landauer time or the semi-classical time, maybe it really does start to come back down. But in parallel, there's this out-of-plane time that's clearly a signature of the quantum regime. It's basically zero until you get below the tunnel barrier. So with a lot of work, David Spearings followed this experiment up. managed to get to much lower temperatures, managed to clean up the barrier, managed to get much more accurate data. And this allowed him to go further below the tunnel barrier and ensure that most of the particles we saw really were tunneling, and do it for two different barrier heights and compare what happened. So here, the red points are showing a 4.7 millimeter per second barrier, indicated here. And the blue points, a 4.1 millimeter per second barrier, indicated here. And you see they both have the same kind of form. They indeed go up. And now I think there's pretty clearly statistically significant evidence that these red points are getting lower as you go down in velocity. Maybe more interestingly, as you go from this 4.7 barrier to a lower one at 4.1, this time jumps up. It takes longer to tunnel through the low barrier than to tunnel through the high barrier. So this agrees with our theory, but we find it a kind of striking effect. I like to call it the red light effect. The idea is that when the traffic light is red, you're unlikely to cross the street, but if you do cross the street, you probably do it really, really quickly. So somehow atoms are like humans that way. They know they don't belong there, so they try to get out as quickly as possible. I don't even think that's a crazy way to put it. I think there is something about that going on there. Anyway, we were very excited. As I said, this was a 20-year quest to measure this at all. But really what we want to do, and we weren't able to do yet, is not just to ask how much time the atom spent, but where it spent its time. I'd like a picture of a trajectory. I'd like to know, does the reflected atom get reflected right at the beginning of the barrier, while the transmitted atom has to go all the way through the barrier? Or do they all go halfway through and then make a choice? Or what kind of a distribution is there? Is there some difference I can put my finger on between how a transmitted atom gets to the far side and how a reflected atom gets reflected? Well, to do this, what we'd like to do is make a very narrow probe. I'd like to take those Raman beams, that probe, that effective magnetic field, and focus them down just at the entrance of the barrier and say, how much time did you spend right at the entrance? Or focus it a little deeper in and say, how much time did you spend there? How much time did you spend right in the middle? How much time did you spend near the exit? So this is our goal. As I said, right now, that 1 micron focus was the best we could do. So either we have to make our tunnel barrier wider, but to do that, we'd first need to get the atoms to even lower temperatures, or we need to develop tricks to focus our probe more tightly than the barrier. And we're working on both directions now, but we don't have either done yet. We do have theory predictions, and this is what they look like. This is a sketch for a 2 micron wide barrier that goes from -1 to 1. And we can begin by looking at the red curve. The red curve is what we predict would happen for reflected atoms. How much time do the reflected particles spend in different parts of the barrier? Well, the answer is simple. Almost all the particles are reflected, if we're deep into the tunneling regime. So asking what do the reflected particles do is almost the same as asking what does the average particle do? Well, what does the average particle do? That's psi squared. That's just the density of particles. We already know the answer. And it decays exponentially as you go into the barrier. On the other hand, if you repeat that calculation and ask just about the transmitted particles, the experiment turns out to be completely time symmetric. I know I fired a particle in from the left, but I know I saw it come out on the right. The Schrödinger equation is time reversible. So there should be just as much effect of that post-selection as of the entrance. And if you look at the math, you see it's really manifestly symmetric. So if you do this calculation for transmitted particles, yes, you find some exponential decay, but on the right-hand side, you find exponential growth. And this is really surprising because it means whether the particle is transmitted or reflected, by these definitions, it spends vanishingly little time in the middle of the barrier. Yes, it does suggest that while the reflected particle only sees the entrance of the barrier and never sees what's on the far side, the transmitted particles see the entrance and they see the exit. It still seems to say that somehow the particle gets from the entrance to the exit without stopping in the middle. And I would love to see this in a laboratory. That's the thing that we really want to probe. So stay tuned. We're going to develop better experiments and do that. There is a little caveat, but for people who are curious, I'll talk about it. We also, of course, wanted to compare the transmission and reflection times. Oh, maybe I should have pointed out. The dirty little secret hidden in this plot may already be clear to some of you. Our current experiment only looks at the integral. It looks at how much total time do you spend in the barrier. These two curves have exactly the same integral. It happens that this amplitude is half of that one. And if you sum it up, you find transmitted particles and reflected particles spend the same time inside the barrier. So for my goal of seeing what's the difference between the two subensembles, that's not the interesting measurement. We need to break it down. All the same, David and the rest of us all thought it would be interesting to compare them, even in the current experiment. And when he did that experiment, he saw something absolutely mystifying. These are plots from our tomography measurements. So the spin density S of X, S of Y, and S of Z across the wave packet. And the different colors are just different parameters, different strengths of the magnetic field. But the details don't matter for us. What matters is that these things have shape to them. They go negative and then positive. They're different in different parts of the wave function. We never expected that. That never happened in our transmission experiments. There was simply one answer to what the spin for the transmitted atom should be. And it turns out for the reflected atom, it's not the same. Different parts of the reflected atom cloud have different spins. Looking at it for a while, we realized this actually had to be due to collisions between different atoms. The atoms are now exchanging spin with one another. And if we do a Schrödinger equation simulation, we don't see any effects like this. If we do a Gross-Pideevsky equation that includes the interactions between the atoms, we get extremely good qualitative agreement, but even some quantitative between theory and experiment. So this is all due to additional interaction effects. And I'm just mentioning it because for the experts in the room, it might be using, we were carefully working in a team where we could neglect interactions. We went to such low densities that we thought there were almost no collisions. And it turned out that in transmission, that was a good approximation. Schrödinger and Gross-Pideevsky simulations agree perfectly. In reflection, life is very different. Once you reflect an atom, it has to fight its way back through the rest of the atom cloud that's still moving towards the barrier. So it turns out even when in one-dimensional propagation, or sorry, unidirectional propagation, you can neglect collisions. Once you add a second momentum component in the opposite direction, you can't do that anymore. So, all right, we hadn't anticipated it. It wasn't a huge shock once we understood it. The huge shock was the following. In rubidium, the atom-atom interactions are almost entirely spin-independent. So we're used to saying that there's no spin-based interaction in rubidium, and yet somehow we get these textures that imply that as you propagate across the cloud, you're exchanging angular momentum. And it turns out that this has to do with something known as an indistinguishable spin rotation effect. We got some help from Joseph Tywissen to really elucidate the theory and make up a full quantum hydrodynamic model or magnetodynamic model for what's going on. It was published last year in Phys Rev Letters. And just again, for the experts, those who are thinking about interacting atom clouds, I'll say there is an indistinguishable spin rotation effect that's well known in a pretty narrow community. And we eventually decided, we're seeing something like that. And as soon as we said it, everyone in that community got angry at us and told us you absolutely can't be seeing that effect because it never occurs in Bose-condensates. It only occurs in thermal clouds. So it was a long journey to really understand what's going on here. The short version of the story, though, really comes down to basic quantum information, quantum interference. If I take two parts of a wave packet with the same spin, I have a forward propagating wave and a backward propagating wave. They form a standing wave. And in a standing wave, there are regions of very high density and regions of very low density. And that enhances the probability of a collision. The atoms collide when they're in a high density region. If, on the other hand, before being reflected, the particle's spin rotates, it can no longer interfere with the incoming wave packet because they're distinguishable, which means there's no standing wave and there's no increase in density. So it turns out that the effect of collisions is greater if you have the same spin in your reflected component than if you have a flipped spin, even though the interaction has no spin dependence at all. So we get an effective magnetic interaction between the atoms purely because of this role, quantum mechanical indistinguishability and distinguishability. All right. Final goal for that experiment, before I shift gears entirely and wrap up, is the question of quantum measurement. Does the very act of looking for an atom inside a barrier modify its behavior? And like so many, this is a picture of two of the students who pioneered our BSc experiment, Mirko Zilka, who actually spent a few years in Singapore at NTU, in Reinhold Dumke's group, and Chris Eleanor, who now has a consulting company. And when the experiment wasn't working at all, they decided to try a last-ditch effort and use a truly Canadian method of cooling our atoms, which is a great photo, but didn't do much more. All right. As I was saying, as many things in physics do, this one stems from a great question at a conference. Bill Phillips tackled me long ago when I said we wanted to very weakly measure what the atoms were doing. And he said, why weakly? What would happen if you did it strongly? And I said, well, if you did it strongly, you collapse the particle to be wherever you saw it, and it's not tunneling anymore. All bets are off. And he said, yeah, of course, I know that. But I want to understand the physics. I want to understand how that happens. And it's been nagging at me ever since. Here's the basic idea. Imagine a particle moving towards a rectangular barrier. But suppose, just for argument's sake, that I was shining light on the barrier at the same time. So the light could scatter off the particle, and I could get an image. And every now and then, I would see a point on the screen over here that would tell me, oh, I saw the particle in the entrance to the barrier. Well, obviously, every time I got that result, I would know that the particle was over here. I would project it onto a wave function localized in the barrier. And once I did that, it wouldn't be tunneling anymore, because if it's in the barrier, it has enough energy to be in the barrier. I would have to give it extra energy for this to happen. The idea that just by looking for particles in the barrier, you could change the tunneling probability is, I think, really beautiful. Notice you don't even need to have the screen here. I don't need to observe the particle. What's important in quantum mechanics is that in principle, I could have observed it. What matters is that I'm shining some sort of a probe on the particles, which would be able to tell on occasion that the particle was inside the barrier. If that happens, then those particles automatically get some chance of getting promoted above the barrier height, which means that no matter how thick the barrier is, they could roll off to the end. So for whatever it is, over 20 years now, in the back of our minds, we've been wondering, could we ever really do that experiment? And a few years ago, we had an interesting idea. I already said all that. And we said, look, we're already doing these little Larmor rotations to do the weak probe. We could imagine doing a 180-degree Larmor rotation. And of course, if I had a really big magnetic field and somehow set it up so that it implemented a pi pulse, then every time an atom saw it, it would flip to the opposite spin. And that would essentially collapse the atom to be in that region. Except there's no way we can set this up to be a pi pulse. There's no definite value to the time the particle even spends in that region. The new idea was to give up on the big magnetic field, go back to these small rotations and say, look, if I begin with a particle polarized along plus x, and it rotates by even a few degrees, there's some possibility that at the far side, I'll find a particle polarized minus x. If it didn't see this magnetic field, it would still be exactly along plus x, and I would never see it minus x over here. So I don't need to do a pi pulse. I could do a 3-degree rotation over here. But as long as I focus in only on the minus x particles here, I'm looking at particles that I know saw that magnetic field. So we said, would that be good enough? Would that collapse the particles to be in the barrier? Could we do a measurement where we look at the minus x particles and we ask what fraction of them are transmitted, what fraction of them are reflected? And what I was hoping is that since the minus x particles had been collapsed, they'd have equal probabilities of being transmitted and reflected. Instead of seeing the exponential decay, we'd see wherever you find the particle, it's got a 50% chance transmission, 50% reflection. So I asked David to simulate this, and he did. And I should have realized what he was going to see, because the experiment I described so far is a time-independent experiment. We have a tunnel barrier, we have a magnetic field. Time-independent Hamiltonian is going to conserve energy. So there's no way in hell that I was going to give that particle extra energy by doing this. And indeed, that's what David found. What he found, this is a complicated plot, plotting the transmission probability to reflection probability ratio, this thing that I wanted to become 1, on a log scale. So this horizontal line would be equal transmission and reflection. And we're plotting it versus the position within that hypothetical 2-micron barrier where we put the probe. So what David discovered is that this is still exponential. If you put the probe on the left, you're very likely to see the particle come back out on the left and very unlikely to see it come out on the right. If you put your probe on the right, you're very likely to see the particle come out on the right and not very likely to see it come out on the left. And if you put it in the middle, you really do get 50-50. And this slope is just exactly the kind of dependence we're used to in tunneling, e to the 4 kappa times this y prime position, where kappa is that exponential decay constant. And it turns out it's really easy to derive this. To me, it's still shocking and still worth demonstrating experimentally, because in a sense, what this is saying is, all right, you saw the particle somewhere inside the barrier. So it's going to have to tunnel out, and it's more likely to tunnel through a short distance than a long distance. But why is it still tunneling? If I saw it inside the barrier, before we argued that anything you found inside the barrier had to have enough energy to be there. And what this calculation shows is, no, this particle is still acting like it doesn't have enough energy to be inside the barrier, and yet it knows where inside the barrier it started. And again, it's not hard to calculate. It's standard quantum mechanics, but intuitively it's surprising to me. And I think the interpretation of why it didn't collapse the way I wanted is what I've written up here. Did I write it there? Yes. What we found when we find a particle along minus x is that it was in the barrier at some point in time. It saw that magnetic field. But I don't know that it's there now. It could have been there a year ago. And finding that a particle has been at x equals 0 at some point in the past doesn't collapse it to a wave function at x equals 0 now. We wanted to collapse it into the barrier at a given time. So we need a time-dependent potential. And of course, that'll solve the problem of giving the particle energy. But the question it opens is, how fast does that probe need to be? How quickly do you need to look for the particle if you want to be sure it's still in the barrier? And that's the latest stuff that David's been calculating. And indeed, he finds with a slow or time-independent probe, you get an exponential. With a faster probe, it begins to flatten out. And when the probe is fast enough, you really do see this flat line at 1. You really do get this regime where you've collapsed the particle to be in the barrier, and transmission and reflection become equally likely. What we don't understand is what determines that timescale. It turns out to depend on exactly how deep into the barrier your probe is. And we can calculate it numerically, and we have some perturbation theory approaches that get it in some regimes. The surprise to me is that if your probe is a distance d from the closest edge of the barrier, I thought either we'll get a constant, or maybe we'll get something proportional to d and discover a new velocity scale, or we'll get something proportional to d squared and discover a kind of diffusion constant. None of those is the correct answer. We see something proportional to the square root of d. I have no intuitive understanding of why the time it takes a particle to leak out of a gap of size d should take a time proportional to the square root. It comes out of the math. We have no intuitive explanation of that. So yet another thing, if it rings bells in anyone's heads, I'd love to hear what it makes people think about. All right, so take a breath, because I know I went through a lot of material there on the tunneling project, and that's why I promised to give one other new experiment. So everything I said, if it made no sense to you or if you forgot it, that's irrelevant now. We can start over. This is an experiment where we're asking not how much time an atom spends inside this light beam barrier, but how much time light spends inside atoms. And it sort of comes from this picture of photons exciting atoms and then getting re-emitted sometime later. I'll be honest, it began as one of our rare attempts to do something practical and useful, figure out how to make 2-photon switches and quantum logic gates, but then we got distracted by a more fundamental question, so we've switched gears for the time being. And the question is this: while a photon traverses a dielectric, piece of glass, cloud of atoms, I don't care, where does it spend its time? Aren't photons supposed to travel at the speed of light? Why does it take longer to get through a piece of glass? If you're like me, you probably heard people when you were an undergrad or a grad student say, oh, the transit time goes up, because although the photon itself travels at the speed of light, every now and then it gets absorbed by an atom and it's trapped, not moving anywhere, until the atom re-emits it. And people argue that in glass, you don't normally think about light getting absorbed because glass is transparent. But of course, there's virtual absorption. Even far from resonance, The uncertainty principle says that for a little time, you can violate conservation of energy. That's not a careful, popular way of saying it, but it's sort of a good hand-waving picture. So that for a time on the scale of 1 over the energy gap, maybe the atom can spend that in the excited state. And it sounds very hand-wavy, but at least the scaling is okay. You all know from the Lorentz model what the index of refraction looks like. Far from resonance, it falls off as 1 over the detuning, 1 over this energy difference. And 1 over the energy difference is what you'd expect from an uncertainty relation argument, right? That delta T should be 1 over delta E. So you might buy this far from resonance. On resonance, where the detuning goes to 0, I obviously don't expect the time to go to infinity. And in fact, the index of refraction goes to 1. So it's natural to say the picture is only good far from resonance. We should try to say something different, closer to resonance. My guess would have been maybe the delay saturates at something related to the width of this transition, related to the lifetime of the atom, or maybe something else happens. Sorry, press too many buttons. Moving forward. Yeah. Turns out it's even worse than that. This is just the index of refraction. But in the formula for the group delay that most of you know, there's also a derivative dn d omega. So right near resonance, where there's this huge negative slope, you get what's known as anomalous dispersion, and the group delay shoots down very often to a huge negative number. So as in the tunneling time I mentioned before, it turns out particles can get out earlier than you expected them, faster than light, or even in negative time. That's been understood for almost a century. It doesn't violate any deeply held convictions, but it sure means we'd have trouble explaining it this way. So we decided we should try to do an experiment. We thought about what's going on with atoms when we shine light through a sample on resonance. And we realized there's one thing we can say rigorously that's pretty simple. If I ask you, what's the probability of an atom being in the excited state? So I can integrate that up and ask, how long did atoms spend in their excited states? At least in the low intensity regime, it's just given by the intensity divided by the saturation intensity. In more simple words, it's given by the number of photons per absorption cross-section per atomic lifetime. That's basically how likely the atom is to be in the excited state. The interesting thing is the number of photons that are absorbed is the number of photons per absorption cross-section, period. Very similar sounding expression, but without the atomic lifetime coming in there. So when you divide the two, if you take the integral of the number of excited atoms and say, well, that's the total time all the atoms put together spent in the excited state, it works out to be exactly the absorption probability multiplied by the excited state lifetime of the atoms. So you look at that formula and you might say there's a really simple way to understand that. You could interpret this by saying some atoms get absorbed. Some photons get absorbed. And again, I didn't specify. We're imagining an experiment 1 photon at a time. No stimulated emission, no multi-photon effects. Just what does 1 photon do? Well, if 1 photon gets absorbed by an atom, I expect the atom to spend, on average, 1 lifetime in the excited state before it spits the photon out in a random direction. But if it spits it out in a random direction, I won't see it transmitted to my detector anymore. That's the lost photon. On the other hand, some of the photons just get lucky and they never get absorbed and they make it all the way to the detector. And that way, the absorbed photons led to a time delay of tau spontaneous. The transmitted photons led to 0. The weighted average is exactly what you expect here. So this is not the right answer. This is what my student Josiah and I expected, and we thought we should probe this experimentally and see if it was really true. And as I'll show you, we were wrong. How did we do the experiment? We went back to these Kerr nonlinearities that we were studying to make our photon logic gates. In our case, we just used a 2-level system in rubidium-85 in this case. And the idea here is that that single photon I send in on resonance could get absorbed and it removes atoms from the ground state. If it removes atoms from the ground state, it lowers the index of refraction seen by this other beam, what we call the probe beam. So we'll see reduced phase shift on the probe beam. depending on how many atoms are in the excited state. That's really what gives rise to these photon-photon interactions, these optical nonlinearities. So we can measure by looking at this phase shift, how long did that pump photon cause atoms to spend in the excited state? And ask, is it only because of the pump photons which were absorbed, or does it also happen even when the pump photon is transmitted? So to do that, we send in a pump photon, but then we add a detector down at the bottom somewhere. And the idea is I can tell whether the photon is transmitted or not by looking at this detector and compare the phase shift over here for the cases when the photon was absorbed and the cases when it wasn't. Here's the schematic of the experiment. We had pulses of not quite single photons, but small photon numbers going through our sample in one direction. We had a phase probe going through in the other direction. There is some trickery that we had to use to isolate the single photon effect. The theory was published a few years later with Howard Wiseman and Mateen Halaji. Happy to talk to people about it, but for now I'm going to sweep it under the rug. Trust us, we had a way of making a measurement of single photon effects. We began by just measuring the classical phase shift. We sent in 20 nanosecond pulses with about 30 photons in each pulse. And you see that there's a few hundred microradian phase shift. Not so hard to measure. It took us some trick getting rid of some other noise sources. But now we need to go and see what's the effect of just the one photon that's transmitted. And the way we do that is we take the difference between the signal we get only on the occasions when our detector fires and the signal we get on all the occasions when the detector doesn't fire. And it turns out that really tells you what's the extra effect of the one transmitted photon. But now we're looking for these very small differences on the order of 10 microradians over 20 nanoseconds between these huge things in the background of all the linear phase shifts and everything else. So I'll just stress Josiah and Daniela and some others, Kyle and Andy ended up helping later on, really spent hundreds of hours hardly sleeping to get this amazing data, not counting the hundreds of hours they'd already spent fighting all the noise sources and making this a clean experiment. But at the end of the day, we looked for something that had the same shape as that cross phase shift. And even though there's a lot of noise here, I think you can pretty clearly see something extra was going on right in the middle. So even though we expected to find zero, this convinced us that no, there's a non-zero effect. Even the transmitted photons really do spend time, do cause atoms to spend time in the excited state. This is sort of one data point on a plot where we'd love to have some theory, except at the time, skip some of the other details I could go through, but I just want to get to the point of saying we had a lot of semi-classical models of what the atoms were doing and how an atom could absorb and then re-emit a photon. But none of those models could actually predict the outcome of our experiment, because our experiment was asking, what is this phase shift when one photon goes here or when one photon goes there? Semi-classical optics has no sense of what one photon going here or there is. We need a model that includes entanglement between these two different optical beams. We need a fully quantum treatment. And we need to do this in a post-selected open quantum system. So it really throws together all the things that we find difficult. And it took us a few years to really figure out how to solve it, teaming up with Howard Wiseman in this case, coming up with a beautiful quantum model that has been on the archive for a few years, but we're still fighting with referees over, and make us feel a lot better about some of our intuitions. What we'd been thinking, for the reasons that I just skipped over, is that, okay, we had a really big OD and a really big bandwidth. And those things make the optical propagation really complicated. And they cause things to happen where the atoms get excited and come back down. But if we went to a very low OD or went to a very narrow bandwidth, life should get simpler, and maybe our original idea would be correct, and we'd see zero excitation time. And indeed, we got to zero excitation time. The problem is, on the way to zero, we get negative numbers. And obviously, when I saw a plot of how much time atoms spend in the excited state and it had negative numbers, I told everyone in earshot, you've done something wrong. I told my students there was a problem with their code, but they proved to me that there wasn't. I told Howard there was a problem with his theory, but he proved to me there wasn't. And after a while, we came to accept it and realized we should have known things like this could happen. They happen all the time in weak measurements and post-selected quantum systems. And this is another example of things we'd kind of seen before. And more surprisingly, when we looked at this slope here, we realized it's basically just minus the lifetime multiplied by the OD, minus the OD times the spontaneous lifetime. And for those of us who've been working long enough with atoms, we look at that expression and we say, oh my God, that's exactly the group delay. From the very beginning, we asked, can you explain the group delay by saying that's the amount of time atoms spend in the excited state? And I said, well, no, of course not, because the group delay can be negative. Well, now it turns out this can be negative too. And our first intuition seems to be correct after all. If you measure weakly how much time atoms spend in the excited state, we really should get this negative number. It should be exactly equal to the group delay. And what happened to the data? There's supposed to be data somewhere. In the very latest experimental result, also on the archive just since last year, Daniela and her co-workers proved that by playing with the bandwidth of the pulse or the duration of the pulse, she could smoothly tune us from a region, like in our previous experiment where the delay time was positive, to one where it was negative. So we really see the nonlinear effect of a transmitted photon on our probe beam can have the opposite sign to the one expected. Instead of looking like it caused atoms to spend time out of the ground state, it looks like it causes more than 100% of the atoms to be in the ground state. Again, we have some hand-waving pictures of how you can think about that, but mostly it's another one of these surprising effects of quantum interference that you just have to accept. So I ran over time, paradoxically, for this talk about negative times. Let me just jump to the conclusion slide and sum up what I think we've seen. In the case of atom tunneling, we've finally been able to measure how much time atoms really spend in the forbidden region. And we measured both the real and the imaginary components, the in-plane and the out-of-plane precession. And we're going to move on from here to try to measure how much time they spend in different subregions of the barrier to really see the distinct histories of transmitted and reflected atoms. We also hope to probe very soon how we can collapse atoms in the barrier and how that gives us yet another timescale for leakage of particles out of a forbidden region. We've also shown theoretically and experimentally now that the time single photons spend as atomic excitations while propagating really is the extra propagation delay you see in the group velocity calculation, even when that time is negative. And that negative number describes all the effects these atoms would have on other probes, other nonlinear optical effects, and things like that. So with that, let me thank you all for being here. Thank you for your attention and apologize again for running late.